Timeless Concepts from Physics Helpline. This is a video tutorial series through which we will sharpen our problem solving skill. First, we will analyze the problem on hand to find the related concepts. Then using these, we will develop a method which will produce the solution. This will help the students aspiring to get into IIT to understand the much needed advanced theories and applications in physics. In this video tutorial, we will discuss a problem on the rebound of rolling bodies. The question is as follows. A symmetric body like a solid sphere, a circular disc, or a ring rolling without slipping on a rough horizontal surface with velocity of center of mass v0 and angular velocity omega 0 directly towards a smooth vertical wall collides elastically with it as shown in the figure. Find the final velocity of the center of mass of the body in the backward direction when pure rolling sets in if the body is a solid sphere, a circular disc, and a ring. Before proceeding to solve the problem, let us recall the related concepts. For a symmetric body of radius r in pure rolling motion, the velocity of its center of mass v0 and angular velocity omega 0 are related as omega 0 is equal to v0 by r. Angular momentum of a body is conserved when the net external torque acting on it is 0. We choose the point of contact as the reference point for the following reason. The two forces acting on the body are weight of the body W and force of friction F as shown. We observe that the lines of action of both the forces pass through the point of contact. Therefore, torque produced by these forces about the point of contact is 0. Hence, angular momentum of the body about the point of contact is conserved. Now, angular momentum of a rolling body is equal to angular momentum of the body about its center of mass due to rotation plus angular momentum of the center of mass about the point of contact due to translation. Now, we are in a position to solve the problem in the question using these concepts. First, let us define the physical quantities necessary to describe the motion of the body. Mass of the body is equal to m, radius of the body is equal to r, radius of gyration of the body about the center of mass is equal to k. Therefore, moment of inertia of the body about its center of mass is I is equal to mk square. When pure rolling sets in finally in the backward direction, let the velocity of its center of mass towards right is equal to v and clockwise angular velocity is equal to omega. Now, let us understand the various significant positions of the body shown in the figure. In position A, the body is rolling without slipping with linear velocity v0 towards left and anti-clock angular velocity omega 0 such that omega 0 is equal to v0 by r. In position B, it collides elastically with the smooth vertical wall due to which its linear velocity is reversed but its angular velocity remains unchanged since the wall is smooth. C is the position of the body just after collision where it moves towards right with linear velocity v0 and anti-clock angular velocity omega 0. Hence, it is no more in pure rolling motion. However, after sliding for some distance, pure rolling sets in. Therefore, D is the position of the body when pure rolling sets in finally in the backward direction. From this instant onwards, the body moves towards right with linear velocity v and clockwise angular velocity omega such that omega is equal to v by r. Now, we will apply the principle of conservation of angular momentum between points C and D of the body. At C, linear velocity is equal to v0 towards right and anti-clock angular velocity is equal to omega 0. Therefore, angular momentum of the body about center of mass due to rotation is equal to I omega 0 which has anti-clock sense, and angular momentum of the center of mass about the point of contact due to translation is equal to mv0r which is clockwise. Therefore, total clockwise angular momentum of the body at C is equal to mv0r minus I omega 0. And at D, linear velocity is equal to v towards right and clockwise angular velocity is equal to omega. Therefore, angular momentum of the body about center of mass due to rotation is equal to I omega, which is clockwise, and angular momentum of center of mass about the point of contact due to translation is equal to mvr, which is also clockwise. Therefore, total clockwise angular momentum of the body at D is equal to mvr plus I omega. Therefore, conservation of angular momentum gives mvr plus I omega is equal to mv0r minus I omega 0. Putting omega 0 is equal to v0 by r, omega is equal to v by r, and I is equal to mk square, we get mvr plus mk square into v by r is equal to mv0r minus mk square into v0 by r. This implies mvr into 1 plus k square by r square is equal to mv0r into 1 minus k square by r square. On simplification, we get v is equal to 1 minus k square by r square divided by 1 plus k square by r square into v0. This is a general expression for final velocity derived for a symmetric body, which can be applied to specific bodies given in the question as follows. For a solid sphere, k square by r square is equal to 2 by 5. Therefore, v is equal to 1 minus 2 by 5 divided by 1 plus 2 by 5 into v0, which is equal to 3 by 7 into v0. For a circular disk, k square by r square is equal to 1 by 2. Therefore, v is equal to 1 minus 1 by 2 divided by 1 plus 1 by 2 into v0, which is equal to 1 by 3 into v0. And for a ring, k square by r square is equal to 1. Therefore, v is equal to 1 minus 1 divided by 1 plus 1 into v0, which is equal to 0. Which leads us to an interesting result. When a ring rolling without slipping on a rough horizontal surface collides elastically with a smooth vertical wall and rebounds, then it would finally stop.